Great. So this is an introduction into the fifth unit, electrochemistry. So within this, we'll generally be considering these two terms, oxidation and reduction. So what are they? Before we get specifically into what they are, we'll consider a redox reaction, which is an oxidation-reduction reaction, which is a chemical reaction in which electrons are transferred between particles. Within the electrochemistry unit, we'll specifically look at the transfer of electrons between different species or different molecules. In general, all chemical reactions do involve a transfer of electrons, but within this unit, we will focus really on those electrons. So if we consider the following reaction in which we have solid zinc reacting with hydrochloric acid, as that reaction proceeds, we'll produce zinc chloride and we'll also produce hydrogen gas as a result. So if we have a look at what specifically happens to zinc during the reaction, so during the reaction, if we specifically look at zinc, zinc starts off as a solid, and it starts off as a neutral atom, meaning it has a charge of 0. As the reaction proceeds, zinc loses 2 electrons and gains a charge of +2. If we have a look at what happens to the hydrogen ions, as the reaction proceeds, we initially start out with hydrogen ions with a 2+ charge. Each hydrogen ion will gain 1 electron, so we'll have 2 electrons gained per hydrogen ion. And we generate hydrogen gas now. And hydrogen gas has a neutral charge on it, meaning it's no charge whatsoever. So within this reaction, we can break this up into what we call half reactions. And these half reactions represent what is happening to one reactant in the overall reaction. So we look at what has lost electrons, and we look at specifically what has gained electrons. So now we'll specifically define what is oxidation, what is reduction. So with oxidation, we define that as a process in which electrons are lost. So in the previous example, where we looked at zinc reacting with hydrochloric acid, zinc was the species that underwent oxidation. As we discussed in the previous slide, zinc started out with a neutral charge, or a charge of 0. As the reaction proceeded, it lost 2 electrons and gained a positive charge. So it underwent oxidation. Reduction is the opposite of oxidation. Reduction now is a process in which electrons are gained. And so going back to the previous example, we had hydrogen ions gaining those 2 electrons that were lost from zinc, and now becoming hydrogen gas with a neutral charge on it. So in any redox reaction, or any reaction where we have oxidation reduction going on, the total electrons gained in a reaction must equal the total number of electrons that have been lost. And this is ultimately one of the key concepts that we'll use going forward in balancing our redox reactions. So total electrons gained have to equal total number of electrons lost. These electrons just don't disappear out into nowhere. So this is Leo. Leo is a lion, and Leo is very useful because he can help remember the difference between an oxidation and a reduction reaction. So if you can remember Leo, and the fact that he's a lion, And what do lions say? Lions, I think they would say roar, but in this case, Leo says grr. So if you remember Leo the lion says grr, you can remember the difference between oxidation and reduction. So the Leo part basically stands for so the Leo part stands for loss of electron is oxidation. And the grr part is gain of electron is reduction. So if you remember Leo the lion says grr, the Leo part is loss of electron is oxidation. The grr is gain of electron is reduction. If you don't like Leo the lion or you have a thing against cats, the other one that you can use is oil rig. So with oil rig, the way that one works is the oil part is oxidation is loss. The rig part is reduction is gain. So maybe a bit simpler. Doesn't involve cats, but still works. So putting oxidation and reduction into play. So we'll look at an example where we have to use this. So in the first example, we're asked to write two balanced half reaction equations for the following equation. So we're asked to take our overall reaction and turn these into half reactions. So first thing that we have to do with this particular example is come up with the ionic equation, the total ionic equation. So you got to think back to grade 11 a little bit and remember what that total ionic equation is. Basically, anything that is aqueous will dissociate into its ions. So for our total ionic equation, zinc solid, we have lead 2 ions in solution. We have as well 2 nitrate ions in solution. And as our products, we have solid lead. Our lead stays as lead. We have zinc ions with a +2 charge on them. And we have our 2 nitrate ions. The next thing that we need to do, once we have our total ionic equation, is come up with our net ionic equation. So for our net ionic equation, we have to remove anything from our total ionic equation that is a spectator ion. So anything that is the same on the product side and reactant side, we have to remove. So in this case, the only thing that is similar is going to be our nitrate ions. Everything else is going to be different. So in terms of our net ionic equation, we'll have our solid zinc plus our lead ions reacting to give us solid lead plus zinc ions. from there, we should be able to come up with the half reactions that we have going on. So the half reactions are going to be based on the total ionic, or sorry, on the net ionic equation that we have. Third thing that we'll need to do is come up with the half reactions for our net ionic equation. So we'll start with zinc, since that's the first thing that we have written. We have solid zinc that starts off with a charge of 0. As the reaction proceeds, we have zinc that now gains a charge of +2. In order for zinc to gain a charge of +2, it has to lose 2 electrons as this reaction occurs. In the second half reaction, this will involve lead. So we have lead ions in solution, and as the reaction proceeds, that lead is going to turn into solid lead, and it's going to gain a neutral charge. In order for lead to gain that neutral charge, it will have to gain 2 electrons in order to cancel out that positive 2 charge. And so this is how we generate our solid lead with a neutral charge on it. So in these two half reactions, we can identify what is undergoing oxidation, what is undergoing reduction. So with the zinc, since it is losing electrons, I think back to Leo, the lion says grr, a loss of electrons is oxidation. So our zinc, in this case, is undergoing oxidation. Since the lead is gaining those 2 electrons, we can say that it is undergoing reduction. And just to note that the electrons must cancel out completely. These are basically the same electrons that are being transferred from one particle to another. So number of electrons that we have on our product side has to equal number of electrons on our reactant side. And when we get into situations where those don't balance out or don't equal when we set up our half reactions, we have to go about balancing them. So what this leads us into is talking about oxidation numbers. So an oxidation number is the charge that an atom in a compound would have if the electron pair in the bond belongs solely to the more electronegative atom. So we basically use oxidation numbers as a system to keep track of electron transfers. So it's kind of an easy way of assigning or an easy way of keeping track of electrons within a compound. So some common oxidation numbers that we can have is that all atoms that are in their elemental form, for example, if we have solid sodium, if we have chlorine gas, chlorine in it, the oxidation number for any element is always going to be 0. So, for example, if we had oxygen gas, the oxygen within that would also be 0. If we had hydrogen gas, the oxidation number for hydrogen in this case would be 0 as well. Hydrogen in all compounds is always going to have an oxidation number of +1. So, for example, in hydrochloric acid, hydrogen will always have an oxidation number of +1. The only exception for this is hydrogen in hydrides. In this case, it will have an oxidation number of -1. Oxygen in all compounds will always have an oxidation number of -2. So, for example, oxygen in water, the oxygen within that compound has an oxidation number of -2. The only exception that occurs is in peroxides when that oxidation number will be -1. For all monoatomic ions, the oxidation number is basically the charge on the ion. So for example, if you have sodium ion with a charge of +1, its oxidation number will be +1. If you have sulfur ion, which has a charge of -2, its oxidation number will be -2. And so the thing that I'd like you guys to keep in mind with oxidation numbers is that the sum of the oxidation numbers in a compound or ion must equal the total charge of the compound. So for neutral compounds, the sum of the oxidation numbers has to be equal to 0. And the ion charge for ions. So for example, just very quickly, for example, with H2O, as we just discussed from the chart up above, oxidation number for oxygen is going to be a -2. For hydrogen, the oxidation number will be a +1. Since we have 2 hydrogens, we multiply that number by 2, and if we take the sum of our oxidation numbers, it will equal 0. So we have a +1 for hydrogen, another +1 for hydrogen, and a -2 oxidation number for oxygen. The sum of those is going to be 0. Water is a molecule with no net charge on it, so it has a neutral charge. So we would expect our oxidation number to add up to 0. So we can use oxidation numbers now to determine what an oxidation number of another atom will be. And we can use the information that we have in our chart to help determine what that oxidation number will be. So in the first example, we'll determine what the oxidation number of carbon is in methane. So if we use methane as our example, and we're asked to determine oxidation number on carbon. So first thing that we'll do is assign common oxidation numbers. We use our chart from the previous slide. So in assigning common oxidation numbers, we know that we know that hydrogen in any compound except for hydrides will always have a charge of +1. In this case, we don't know what the oxidation number is on carbon, so we are going to assign that a value of x. That's what we're trying to figure out. The second thing that we're going to do is we have to keep in mind that the total charge of the oxidation number has to equal the net electric charge on the molecule or ion. So in this case, methane is an electrically neutral molecule, meaning that it has an overall charge of 0. So what that means is that the oxidation numbers for carbon and hydrogen must equal 0. So the sum of those oxidation numbers for carbon and hydrogen have to be equal to 0. So based on this, we can set up an equation to help us figure out the oxidation number of carbon. So in this case, the oxidation number of carbon, which we've said is X from the top there, plus the oxidation number of hydrogen, and we have 4 of them, so we have our 4 hydrogens, times the oxidation number of each hydrogen, which is plus 1. The sum of carbon plus hydrogen must equal 0. So we can set up an equation now to be able to solve for that oxidation number on hydrogen, or carbon, sorry. And the last thing that we're going to do is we can use some algebra now to determine the oxidation number of carbon. So in this case, when we solve for x, we will get x equaling -4. Indicating that the oxidation number for carbon is going to be -4. So in this case, with CH4, oxidation number above hydrogen, or for hydrogen, is going to be +1. For carbon, it is going to be -4. In the second example problem, I'll let you guys give this a go, but basically it's asking for the oxidation number of sulfur in sodium sulfate. The oxidation number that you guys should come up with is a number of +6. So give that a try, see if you can work that out, and it's done in much the same way that we did the previous example. So we can solve for oxidation numbers. That's great, that's fantastic, but ultimately, why do we do this? Why do we care? Well, using oxidation numbers is, like I said, a system of keeping track of electrons, and it's also a way of telling us whether something has been oxidized or reduced. So using these oxidation numbers now, so an increase in oxidation number indicates that an atom has lost electrons and is therefore oxidized. So if, for example, we start with an atom with a neutral charge on it, and it now gains a charge of +2. This increase in oxidation number indicates that it has lost electrons. If we have an element that, for example, starts again with a neutral charge or an oxidation number of 0, and now acquires an oxidation number of -2 over the course of reaction, this indicates that it has gained electrons and has undergone reduction. So in the following example, we have zinc plus copper sulfate reacting to give us zinc sulfate plus copper. And before we just quickly work out that example and figure out what's undergoing oxidation, what's undergoing reduction, conversely speaking, if we have a decrease in oxidation number, like I said, that indicates an atom has gained electrons and has therefore been reduced. So in the following example with zinc and copper sulfate, without going through all of the steps before and determining total ionic equation, net ionic equation, basically our spectator ion is going to be the sulfate ions. And what we have reacting is the solid zinc plus copper 2 ions reacting to give us zinc ions and solid copper. So if we go through the steps of assigning oxidation numbers for each of our elements, so in this case we have elemental zinc. Anything that is an element automatically gets an oxidation number of 0. We have copper 2 plus ions. Anything that is an ion gets an oxidation number the same as its ionic charge. So in this case, copper will have an oxidation number of +2. Zinc has a charge of +2 as an ion, so it will get an oxidation number of +2. And we have solid copper or elemental copper, which has a neutral charge on it. So if we have a look at what's going on with zinc, so with zinc, we are starting at an oxidation number of 0, and we are increasing to an oxidation number of +2. So this tells us that zinc is undergoing oxidation. If we have a look at copper and what's going on with copper, copper is starting at a +2 and it's decreasing its oxidation number to a 0. So because its oxidation number is decreasing, we can say that copper is undergoing a reduction. So it's gained some electrons from this reaction. So in the following example, you're asked to identify the oxidation and reduction in the reaction of zinc metal with hydrochloric acid. So first thing that we'll need to do is come up with a balanced chemical equation. We're told that we have zinc metal. Anytime we have a solid zinc metal or any type of metal, it's in its elemental form. This is reacting with hydrochloric acid, which is going to be an aqueous solution. This is going to give us zinc chloride, it's an aqueous solution, plus hydrogen gas. Now we just need to make sure that our reaction is balanced. The 2 in front of the HCl will do that easily. The next thing that we need to do is get the total ionic equation. So we'll have solid zinc reacting with hydrochloric acid, which will dissociate into hydrogen ions and chloride ions. This will produce zinc chloride, which will dissociate into zinc 2+ ions and 2 chloride ions. And we have our hydrogen gas being produced. So we'll remove our spectator ions to come up with that net ionic equation. So we have solid zinc reacting with hydrogen ions, giving us zinc ions, zinc 2+ ions, and hydrogen gas as one of our products. So now that we have our net ionic equation, we can go ahead and assign oxidation numbers. So we have elemental zinc. Anything that's in its elemental form gets an oxidation number of 0. We have hydrogen ions. Each hydrogen ion will just have a charge of +1, so same charge as its same oxidation number as its ionic charge. So that means zinc will have an oxidation number of +2, and with hydrogen, since it's in its elemental form, it will get an oxidation number of 0. So now if we examine our different elements, with zinc, we are going from an oxidation number of 0 to +2. So it is losing electrons, so that indicates that our zinc is undergoing oxidation. With hydrogen, we are going from an oxidation number of +1 to 0, so that oxidation number is decreasing, which means it is gaining electrons, and since it's gaining electrons, we can classify it as undergoing a reduction reaction. And so now we've classified, we've identified the oxidation and reduction in the reaction. In the second example, I'll let you guys work that out. But in the second example, you're asked to identify the oxidation and reduction in the reaction when natural gas burns in a furnace. And you're told that carbon dioxide and water form. So in this case, I'll give you guys the unbalanced equation. So you have natural gas, obviously has gas. This will produce carbon dioxide and H2O. So in this particular example, you will not well, you cannot come up with a net ionic equation or even a total ionic equation. These will not break apart into ions. So you have to balance the equation and then assign oxidation numbers. Basically, and you have to identify what is essentially changing oxidation numbers. So we'll work through this one quickly, but assigning oxidation numbers, so within methane, hydrogen will have an oxidation number of +1. For carbon, we don't know what its oxidation number is within this particular compound, so we'll assign it a value of X. And in balancing this out, we're move on. We have a 2 in front of the oxygen and a 2 in front of the water. Everything's balanced. So back to assigning oxidation numbers. For oxygen, since it's in its elemental form, it will get an oxidation number of 0. For carbon dioxide, oxygen will have each oxygen will have an oxidation number of -2. For carbon, we don't know what it will be, so we will assign it an oxidation number of X for the moment. And within water, oxygen will have an oxidation number of -2. Each hydrogen will have an oxidation number of +1. So what we'll need to do then is figure out the oxidation numbers for carbon. So for methane, it is a neutral molecule. So the sum of the oxidation numbers for carbon plus that of all of the hydrogens in the compound should equal 0. So for carbon, we'll get an oxidation number of -4. And when we come to carbon dioxide, again, it's a neutral compound, so the sum of its oxidation numbers should be 0. So the sum of the oxidation number for carbon plus the sum of all of the oxidation numbers for oxygen should be equal to 0. And so for carbon, we get an oxidation number of +4. So if we have a look in terms of what's changing oxidation numbers and what's not, if we look at hydrogen, hydrogen has an oxidation number of +1 on the reactant side and a +1 on the product side. So nothing's happening there. If we have a look at carbon, we'll line up our carbons. Carbon goes from a -4 to a +4. So in this case, carbon is losing electrons as it gains that positive charge. So in this case, we can say that carbon is undergoing oxidation. If we have a look at oxygen, and we can have a look at both oxygens in this case, on the reactant side, it starts off with an oxidation number of 0, and then gains an oxidation number of -2 for each compound. So in this case, oxygen is gaining electrons, and since it is gaining electrons, we can say it is undergoing a reduction. So, so within this particular reaction, carbon is undergoing oxidation, oxygen is undergoing reduction. Alright, so what I'd like you guys to work on is on page 659, questions 12 to 16, page 662, questions 18 to 20. And that's in the attached textbook pages that I've included within the note that you guys have.